Hello. Today I'm going to be going over a lab from Understanding the Principles of Organic Chemistry, a laboratory course by Peterson and Myers. This is lab 36 in the book, the one about chemoselectivity and transfer hydrogenation reactions. So, kind of the purpose of this lab was to look at various reactants. This is reactant A from the lab, and then you would try to do the experiment, and then using NMR and mass spectrometry, we would try to analyze which possible products we got. So the kind of reaction that we are looking at here, this is fluorocinamic acid, and we add ammonium formate, palladium catalyst, and then methanol, and reflux that afterwards. You would get one of two products. It would either be the one on the top with the fluorine still attached, or it would be the one on the bottom that the fluorine does not appear on the molecule. So why this is because in the ammonium formate, there's the H2, so you might recognize a reaction from courses such as DREA, the hydrogenation reaction. Basically, it turns this alkene, the most obvious one, into just two sp3 carbons, right? Originally, there's only one hydrogen here, but basically, you would add the hydrogens to that alkene. But in this particular case, it's also possible for halogens to be removed. So if we had a chlorine as well, I think that's one of the other molecules. If you had a chlorine, let's say, then it also there's a chance that the chlorine will be removed. But according to your lab, you should see that while the chlorine molecule was in fact removed from the final product, the fluorine one didn't. So this is the major product that we see from the lab, and we can confirm with the NMR spectra, mass spectrometry as well. So we'll be going over basically just the HNMR, CNMR, and mass spec. So this is the HNMR of the starting reactant. I've kind of put together a slide with the spectra itself, but then also table 8.7 from the book. This is the table of coupling constants. And I've just jotted down a few notes about what's kind of interesting in the molecule and how we can identify the peaks. So, first off, we should see the molecule here. It's been labeled in this way. Because of the symmetry, we can tell that down here these two are also A and B. So proton E, because this is HNMR, we're looking at the hydrogens, so proton on E is part of the OH group, and we know that this is going to be a broad singlet on the diagram, so it can appear anywhere, but it's just going to be a broad singlet. Protons C and D are part of the alkene, and then protons A and B are part of the aromatic ring. One thing to note is for protons C and D, you can use resonance, and you can find out that C should be a D shielded, because what you get in the end is the aromatic ring, F, but now you have positive charge, and then you have something like that. This is the resonance structure, and because this one is now positive, this is D shielded, and what D shielded means is that it has higher ppm on the spectra. So keeping that in mind, we're going to expect that because proton C is D shielded, it has higher ppm, and also that C and D both have integral 1H, because remember, this is the starting material, there's only one hydrogen on those two carbons. Right. So from that, we can tell, first off, let's try to find the broad singlet. So broad singlet is going to be all the way down here. This is, it's also the highest one, but if you look at the integral value, it's kind of hard to see. The integral shows it's 1. If we look back onto the starting material, there's only one of them there. So this one should be E. Alright, then we're stuck with the rest of the peaks. There's a hint to use coupling constants, so that's kind of what we used. If you find the coupling constant of each peak, you'd find that this one, the one in orange over here, has 5.6, one over here is 8.8, and then the two pink ones are around 16 hertz. So again, how to calculate coupling constants is you take like two peaks. For example, on this, what looks like a triplet, you take these two peaks, and then you'd find their like hertz, and then you'd subtract it. So for that one, I used these two values. Right, they're both around 7.15 ppm. The middle one is like exactly in 7.15. Then the one on the left is 7.17. So you'd find those two hertz values, you'd subtract them, and then you get the coupling constant from that. Right. So knowing the coupling constants, we look back to table 8.7. Here it's shown the like fluorine coupling. Because our fluorine is still here, right? Then we can look at these types of coupling for hints, and we find that in the ortho position. So remember, for aromatic molecules, ortho is here, meta is here, para is over there. For the ortho position, we are going to get coupling constants of 6 to 10. So 8.8 falls within that range of 6 to 10. So this one is going to be A, because A is ortho to fluorine. Right. Then we look at this one, the orange. Same thing here. To find coupling constants, we'd get these two peaks and then find the difference. So this ends up being the 5.6 peak. If we look back onto the table, it's these two that I've marked in orange. But because the constant is 5.6, our table shows us that between 5 to 6 is going to be meta positioned, then that peak should correspond to B, because the coupling constants match. Now for the remaining two, we notice that they're actually around the same coupling constants, 16. If we think back, that means like in an earlier lab we should have seen differences between trans and cis alkene, like their coupling constants, but we see that in a trans alkene the coupling constant should be around 11 to 18 hertz. So 16 falls within that range. We can pretty much say that these two peaks, the ones marked in pink, are belonging to that alkene. And because we've said earlier that proton C is D-shielded and has higher ppm, we will assign the one on the left as C, then the last one as D. So this is H NMR of the starting material. Right. Then we move on to H NMR of the product. Again, same labeling. A, B are going to be the same over here. This time, though, notice that C and D are no longer on an alkene. They're just on sp3 carbons, and because they're on sp3 carbons, we kind of expect them to be on the lower ppm side, so kind of to the right of the spectrum. Again, E is still on the OH, so E is still that broad singlet. And then we can kind of look at the last two peaks over here. These are zoomed in from those two. And we calculate coupling constants again. These are same process as last time. So for the green one, we have coupling constant 8.9. They're marked on that coupling constant table that's been provided. And for the orange one, I did not really mark it on the table, but you'd use the values of this one, and then 4.7.4. So you notice they kind of match up to the ppm, right? This peak is 7.24 ppm. The one next to it is 7.23. Right? The difference between them is 5.7 hertz. So similar process to the last HNMR. First we assign E as that broad singlet there. The two peaks that we the coupling constants for, because 5.7 falls in the range of meta position, then we're going to say that that one's B. And then 8.9 falls within 6 to 10, so this one is going to be ortho, which is A. And for the last two peaks down there, we can just group them together and call them C plus D because those are both the sp3 carbons. Right. So these were the two H NMR things. By looking at the NMRs as well, you might notice that like B and A for both of those spectrums, they're kind of complicated. Let's see. Like they're more so complicated than you would think. That's because fluorine itself is NMR active, and because fluorine is still within like both the starting and the final product, then we can say that the fluorine is affecting the H spectrum, and that's kind of proof that the fluorine was not removed after we did the entire reaction. On that note, fluorine also affects the CNMRs, so this is CNMR of our starting material. And if we look at the diagram again, because it's symmetrical, A, B are over here. We were given the hint though that all aromatic carbons are coupled with the fluorine, so we should note down A, B, C, and D are the aromatics. But basically, they're not going to have singlets because they're coupled with fluorine. So with that in mind, let's take a look at some of the identifiers of this molecule again. First off, G. G is part of a carboxylic acid or a carbonyl. But either way, it's going to be really high ppm. So it's probably the leftmost peak on our molecule. E and F are part of a transalkene. And D over here, this one doesn't have any hydrogens. Like most of the other carbons will have hydrogens attached to them, especially the aromatics, but D is the exception. D does not have it. And those are most of the identifiers. So if we look at the NMR spectrum, you can see leftmost one. We've said that that's probably going to be the G carbon, the one that's part of the carbonyl, carboxylic acid. So we assign this one as G. And then we try to look at what other ones we might be able to assign. If you notice, A, the proximity of carbon A to fluorine, kind of, we might expect that to be relatively high ppm as well. So when we look down here, if you decide to take the coupling constant of these two peaks, you might notice that this gives us 248.3. It's because we're using the two highest ppm values over here. It's marked in green. But yeah, that difference ends up being 248.3 hertz. Now, if we go back to table 8.7 in the book, 248 hertz falls within the range 240 to 300. And that suggests that we're actually seeing FC coupling, where the C is adjacent to the fluorine molecule, atom. So that suggests to us that if we look on the diagram, the fluorine, the carbon that's just adjacent to it, is going to be A. So this is heavily suggesting that this is the A carbon. Yeah, so this one's kind of weird. We have two peaks. It looks like they're just two different carbons, but coupling constant kind of shows that that's actually the same carbon, and it's carbon A. Alright, so then we look at the remaining peaks. Because A, B, C, D are aromatics, right? We expect those not to be singlets, so the ones that aren't singlets are this one, they're both the zoomed in peaks over here, and also this very last one here. So if we look at the rightmost peak, take the coupling constant, we get 21.8 hertz. It's marked on the diagram on the table as those two. And 21.8 hertz falls within the range of 10 to 45. That suggests to us that this is FCC coupling. And okay, let's clear up this diagram a bit. FCC coupling shows FCC. This is going to be carbon B. So we expect S1 to be carbon B. Okay, so we have those two peaks down, they're part of the aromatics. Let's try to just look at the rest of the aromatics. Notice that D, I said before, does not have hydrogens attached to it. Usually what that means is it has lower integrals on CNMRs. Just in general, if you have a CNMR and there's a carbon that doesn't have any hydrogens on it, usually that's the lower integrals. So if we look back to our doublets, or well, the things that aren't singlets, right? You notice that this one is the lowest integral peak, and so we assigned this one to D. Now that leaves the last aromatic one, and we put that as C. Right. And then we're left with the alkene. For this one, we just group them together. E and F are just going to be those two. So this is the CNMR of the starting material. Clean it up a bit. I do want to note that the way I've drawn it might be kind of confusing, but I've tried to color code it. The pink ones are these peaks, just these two. They don't include the ones over here. The purple ones are the ones that have been zoomed in a bit. So these D and C, they are part of just these two peaks. Right. Okay, so this is CNMR of starting material. We'll move on to CNMR of the product. Again, let's look at what's identifying. Again, we have A, B, C, and D again being part of aromatic. So A, B, C, D, aromatic. They are, again, coupled by fluorine. So we're expecting them not to be singlets. And we can see through the zoom-ins already that, yeah, we're seeing the things that aren't singlets again. Okay. G, again, part of a carboxylic acid, carbonyl. So we expect that to be the leftmost thing. And this time, kind of interesting is we're noticing this really complex peak. I'm not going to identify it, but it's just way more complicated than we're expecting anything. So this is actually a solvent. And if we look in the book, forgot which table, but there's a table of solvents. This is going to correspond to one of the solvents. This is a solvent. Okay, that leaves us with the rest of the peaks. And again, we use coupling constants. So starting from this one, last time in the starting material we saw this one's A, and well, if we take coupling constant again, 241.6, 241 falls within range 240 to 300. This is FC coupling. So that's corresponding to carbon A. Carbon A. Okay. Then again, D last time and still now has no hydrogens. We expect this to be the lowest integral. So if we look at the not singlet things, they're all zoomed in, so it's kind of misleading. So just look at like the peaks themselves. This one shows us the lowest integral. We expect this one to be D. That leaves us with two more. If we take this one, the peak on the right, zoomed in peak on the right, if we take that coupling constant, it gets us 21. 21, it falls within range 10 to 45 from our book, so that's going to show us FCC coupling. If we look back to the diagram, FCC, this is going to be carbon B, so this is the B peak. And that leaves us with the last, like, not non-singlet thing as being carbon C. Okay. Then, well, it's pretty obvious, but the last two peaks are carbons E and F. If you look at the label diagram again, and remember that because this is our product, then these E and F are supposed to be sp3 carbons because we did the hydrogenation. So because they're sp3, we expect them to be very low on the CNMR. So these last two peaks we grouped together and we just called them E and F. Right. So this is the CNMR of the product. Yeah. So I think these NMRs, right, one of the main goals of the experiment was see which product we got. But because, especially in the CNMRs, right, we're seeing things that aren't singlets, we know that this is being affected by fluorine. So it's proof that the fluorine managed to stay on even after hydrogenation, and that the only thing that really changed was the alkene turned into like just two sp3 carbons. Lastly, one thing we were supposed to learn is how to kind of basically read mass specs. So mass ions, this is part of the mass spec technique, but mass ions are basically your entire molecule minus one electron. So what we have, normal oxygen, you have 4 electrons. If you take out one, then it becomes positive charge. So this is our molecular ion of the starting product. If we calculate its molar mass, it's going to give us around 166 grams per mole, or AMU. And on the mass spec, the peak that matches the molecular mass is going to be referred to as what's known as the molecular ion peak. So this is 166. That's molecular ion peak. And then another identifying peak is the base peak. This is just the highest peak, and that shows us like the most frequent form of the molecule. So in this case, for our starting material, the base peak and molecular ion peak are the same thing. That's how we label them. If we go to our product, then notice that here we have kind of a different diagram. If we draw out the product molecule, remember this one is the one without the alkene. Then we have 2 extra H's compared to the original one, so our molecular mass is going to be like 168 grams per mole, 168 AMU. So this refers to this peak, that's the molecular ion peak, but this time our base peak is different. The base peak is now separated. So yeah. So this has been kind of a run through of the mass spec, the NMR spectrums from lab 36, the Chemoselectivity lab for fluorocinamic acid. Main goal was to see that which product we made, and through our NMR analysis we can tell which peak is which. We can tell that fluorine is part of it. We can tell like differences between before and after the hydrogenations. So yeah, hope it's been helpful. I'm just quickly going over all the slides, taking off the markings in case you want to take one last look at them. And yeah, thanks for watching.